In the last few videos, we've been talking about spherical coordinates and changing from rectangular into spherical as a method of simplifying triple integrals that involve spheres or cones or things like that. And how we were doing that is as we were transforming our integral from xyz into rho theta phi, we had to insert this new factor, which I've been referring to as the Jacobian. In this video, I want to define what is the Jacobian, where does that come from, and why. And in another video that we just went through, we talked a little bit about the generalization of transformations, where if we're going from one region to another in space, a transformation is just a two-dimensional change in variables, where say we're starting with u and v and going into x and y, or vice versa. What can happen with nonlinear transformations is our rectangular region can morph into this sort of parabolic region. And in a linear, I talked a little bit about linear transformations where the transformation doesn't actually change the shape, but it just sort of stretches and skews. Yes. And also one idea that I was starting to talk about is how do we change our variable from dA into the terms of the new variable? We have to compensate for this kind of manifestation, this change in area between the regions. And all of that is solved by the Jacobian. There is a general way of doing this, of solving the transformation, and it's kind of analogous to when we're changing dx into du over minus 2 in that example, figuring that out, or when we're changing dx dy into rd theta. All of those transformations can actually be generalized. Let's look at our textbook's definition of the Jacobian. So it says, sorry, it's a little bit fuzzy for some reason here. My slides look more clear down here. I don't know why. It's good enough. But it says the Jacobian of transformation t is given by x, g, u, v, and y equal h, u, v. Kind of like in the last example, we can let x and y be any transformation in terms of u and v. And it says the partial differential with respect to x and y divided by the partial with respect to u and v. Essentially, this is just a notation that's used for the Jacobian, the change in variables between things, is defined to be the determinant of the partials of that transformation. So notice in this matrix, we're using dx du, dx dv, dy du, dy dv. From those equations, we could take those partial derivatives, take the cross product, or whatever you want to call it, the determinant, the difference between those products, to solve what our Jacobian would be. And if we look at the formula for the change of variables in a double integral, it says, suppose that t is a C1 transformation whose Jacobian is non-zero, and that t maps a region S into UV plane onto a region R in the XY plane. So essentially, in the previous example, we looked at where there was a weird UV region that mapped into a new region in the XY plane. Suppose that F is continuous on R, and that R and S are type 1 or type 2 plane regions. Suppose also that T is 1 to 1, except perhaps on the boundary. Then, essentially setting up all of the small details of how this all works, the double integral across the region of our function with respect to the area is going to be the new integral, where we're substituting in our transform variables for u and v with respect to u and v. And notice that we have this Jacobian inserted into the integral. Kind of like what I was saying, is it's our magical number or functional transformation from xy into uv for any scenario. Let's do a couple examples, because it all can get very abstract. But for example, let's say we wanted to find the Jacobian of this transformation. And again, looking at our visual of what that was, say we wanted to solve this integral. This integral is a lot easier in terms of u and v. What sort of multiplier would we need to compensate as we go from one to another? It essentially involves the partial derivatives of those variables. So let's write it all out. But basically, we would need to know, well, what is dx du? And so if we're looking at our x variable, well, differentiating partially, well, derivative of this with respect to u, treating v as a constant, we get 1 plus 0. So we're going to have 1 here. Not too bad. And we could also do dx with respect to v. That's also going to be 1, treating u as a constant. Not so bad. And often the Jacobian may be relatively straightforward. It just kind of depends on the transformation. And the beauty of the Jacobian is whatever the transformation is, you can use the Jacobian to solve it. In other words, it's kind of like when you're changing from x into u. We got to figure out how to do that. The Jacobian always will do that for us, which is why it's such a powerful idea. Now for our dy dv, with respect, sorry, let's start with u first just to keep our structure the same. We'd have 2u, and again, treating v as constant. Now partially differentiating y with respect to v, we would have 0 minus 2v. So summarizing, we have our transformation. We need to know the partials of both variables of the transformation. And it says the Jacobian, and this is just a notational thing for the Jacobian, which will represent the change in variables for our double or triple integrals if we were to do a 3-variable transformation, which we'll look at in a second. And it says, again, it's going to be the determinant of, we're just going to put those things into matrix. And again, to solve the determinant of a 2x2 matrix, we can just take these cross products and go through like so, right? So we're going to have negative 2v minus 2u. In summary, this will be what we call the Jacobian. Now, also, one other thing to notice, say we wanted to solve a hypothetical integral, this is going to be what I need to substitute in as a multiplier in here. But also notice that there's actually an absolute value sign on here, because I know we use the straight bars to represent a determinant, but it's actually the absolute value of the determinant. So it also depends on whether u and v are positive and negative, but in that example, u and v were strictly positive and negative. So if we take the absolute value of this, we'd have a strictly positive value, right? 2v minus 2u. But sometimes you need to be a little bit careful, algebraically speaking, about how you do that change in variables, because usually absolute value, you can't just cancel it out to make it positive. But since u and v were strictly positive, we need to make sure that is always positive. Let's also do another example, because in previous, going back into polar coordinates, I discussed a little bit in class about why x and y, as we shift into polar coordinates, need to change into r dr d theta. But it turns out we can use our definition of transformations in the Jacobian to actually do all this. Because again, we have our transformation of x and y as, and not u and v, but functions of r and theta. And what we could do is look at, well, what is dx dr? What is dx d theta? What is dy dr? What is dy d theta? And each of those things, well, dx dr would just be, well, derivative of r is 1. I did not give myself enough space here, did I? Wonderful. Dx dr would just be cosine theta. Dx d theta, excuse me, the derivative of x with respect to theta, well, derivative of cosine theta is negative sine theta. And then dy dr is going to be sine theta. Dy d theta, again, would be cosine. So r cosine theta. And it turns out, well, if we want to solve what our change in variables must be from dA into terms of r and theta, we already know the answer here, but we're essentially just verifying this is the same change in variables that we did geometrically or trigonometrically. So again, if we were to write this out, we'd have dx dy in terms of, usually we'd write r and theta in this way, right? Because that's a typical way we write polar coordinates. Again, would be the determinant of the product of those things. So dx dr. Another way to read this is it's this one, vertically, and then this one horizontally. But basically x over r, y over r over here. And make sure I got these things in the right place. No, I do not. So that's kind of what I was saying to be careful about. Because when you're using u and v, you can just straight use the thing. But notice that the top line must be both of our x's. So the way I had it was good to begin with. But it's good to verify and make sure we got things in the right place based on the definition. And anyways, if we make this determinant here, well, we're going to have r cosine theta squared, and then minus a negative r sine theta squared. So double negative would make positive in the cross product here. Let's move this so you guys can see it. Sorry about that. Minus double negative r sine squared theta. So plus r sine squared theta. And what you notice is, well, we have a cosine squared plus sine squared, factor out the r. This is just going to be r. And summarizing, when we try to plug this in our Jacobian, our transformation, if we're working into a triple integral in terms of a function of r and theta, a dr and d theta, it would just be r times dr d theta, technically with an absolute value. But as we said, usually we assume that r is positive to begin with in our construction. But sort of summarizing, if we want to know what that change in variable from, dA into anything, the Jacobian is the magical link that connects the dots between x and y into any transformational variable. And it does indeed work. Now, if you're wondering more about the theory of y, well, that's a little bit beyond the scope of complexity for our course because it takes some linear algebra and some other stuff, but it is an interesting idea which I'd say you guys think about on your own. And in the next video, what we'll do is we'll look at for spherical coordinates. We've been using this magical rho square sine phi as our transformation. Let's actually see why in the next video.